This is the video for Part 2 of Section 1.3, Primes and Unique Factorization. In this video, we're going to examine the fundamental theorem of arithmetic. As mentioned at the beginning of this section, the primes can be viewed as the building blocks of the integers. That is, every integer except for 0 or plus or minus 1 can be factored as the product of primes. For instance, 60 is equal to 2 times 2 times 3 times 5, where 2, 3, and 5 are all primes. In this context, a prime can be viewed as a product with just one factor, namely itself. So 71 is a prime, and so its factorization as a product of primes would just be 71. Otherwise, we would need to say that every integer is a prime or a product of primes, and it's just easier to allow for products to consist of a single factor. So first we're going to prove Theorem 1.7, which states that every integer n except 0 or plus or minus 1 is the product of primes. To prove this, we want to first show that it suffices to prove the theorem in the case that n is a positive integer. So let's suppose that n is an arbitrary negative integer with n not equal to negative 1. Then minus n will be a positive integer and n will not be equal to 1. And if we can show that minus n is a product of primes, say minus n is equal to p1 times p2 down to p sub k, then n will be minus p1 times p sub 2 down to p sub k, and this will imply that n is also a product of primes. So since p1, p2 down to p sub k are all primes, then minus p1, p2 down to p sub k will also be primes. It follows that we only need to prove the theorem in the case that n is positive, so that n is actually greater than 1. We then need to prove the statement for all n greater than 1, n is a product of primes. As a reminder now, a product of primes may include a single factor. So when we say that n is a product of primes, it includes the case that n is itself a prime. So to prove this statement, we'll use a proof by contradiction. So we suppose the statement is false, which means that the negation is true. The negation will be there exists an n greater than 1 such that n is not a product of primes. Suppose then there exists a positive integer greater than 1 that is not the product of primes. We then need to derive a contradiction. So let's let S be the set of all positive integers greater than 1 that are not the product of primes, so that S is the set of n greater than 1 such that n is not the product of primes. Then S is a subset of the set of positive integers, and since we are supposing that there exists a positive integer greater than 1 that is not the product of primes, then the set S is not empty. So then the well-ordering axiom implies that S has a smallest element n sub 0. Since n sub 0 is in S, then n sub 0 is greater than 1, and n sub 0 is not the product of primes. Now since n sub 0 is not the product of primes, then n sub 0 is also not itself a prime, and therefore n sub 0 is composite. Now since n sub 0 is composite, then it has a positive divisor a other than 1 or n sub 0. Since a divides n sub 0, then n sub 0 is equal to ab for some integer b. Now since a is not equal to 1 and a is not equal to n sub 0, then b is also not equal to 1 and not equal to n sub 0. It follows that both a and b must be strictly greater than 1 and less than n sub 0. Since n sub 0 is the smallest element of S, and a and b are both less than n sub 0, then this implies that a is not in S and b is also not in S. Therefore, both a and b must be products of primes, so that a is equal to the product p1, p2 down to p sub s, and b is the product q1, q2 down to q sub t for some primes p1, p2 down to p sub s, q1, q2 down to q sub t. But then n sub 0 equal a times b implies n sub 0 is equal to the product p1, p2 down to p sub s times the product q1, q2 down to q sub t. And this implies that n sub 0 is a product of primes. This is a contradiction since n sub 0 belongs to S, and S was the set of integers greater than 1 which are not products of primes. And thus the result is true. So every positive integer greater than 1 is a product of primes. Now the theorem tells us that every integer has a factorization as a product of primes. In general, a composite integer can have different prime factorizations. For instance, 60 can be written as 2 times 2 times 3 times 5, where 2, 3, and 5 are all primes, but it can also be written as minus 2 times minus 5 times 3, where minus 2, 2, minus 5, and 3 are primes, and it can be written as minus 3 times 2 times minus 2 times 5, where minus 3, 2, minus 2, and 5 are primes. But examining these three possibilities, we see these are all essentially the same, differing only in the order of the factors and the insertion of minus signs in some of the factors. The next theorem tells us that the prime factorization is unique up to these two possibilities. And this is Theorem 1.8, which is called the fundamental theorem of arithmetic. Every integer n except 0 and plus or minus 1 can be written as a product of primes. This prime factorization is unique in the following sense. If n is equal to the product p1, p2 down to p sub r, and n is equal to the product q1, q2 down to q sub s, with each p sub I and q sub j prime, then r is equal to s, that is, the number of factors is the same, and after reordering and relabeling the q's, we obtain p1 is equal to plus or minus q1, p2 is equal to plus or minus q2, all the way down, p3 is equal to plus or minus q3, all the way down to p sub r is equal to plus or minus q sub r. So each prime in the first factorization is the same as the prime in the second factorization up to a plus or minus sign. To prove this, first note that the first statement holds by Theorem 1.7, that every integer n greater than 1 can be factored as a product of primes. It remains only to show that the prime factorization is unique. So let's suppose that n is an arbitrary integer not equal to 0 or plus or minus 1, and suppose n has two prime factorizations as listed in the statement of the theorem. So n is equal to p1, p2 down to p sub r, and n is equal to q1, q2 down to q sub s, with each p sub I, q sub j prime. We need to show r is equal to s, so the number of primes in each factorization is the same, and after reordering and relabeling the q's, we obtain p1 is plus or minus q1, p2 is plus or minus q2, all the way down to p sub r is equal to plus or minus q sub r. Well, since n is equal to p1, p2 down to p sub r, and n is equal to q1, q2 down to q sub s, then setting these equal to one another, we obtain p1, p2 down to p sub r is equal to q1, q2 down to q sub s, which implies that p1, since it divides the left side, must divide the right side. So p1 divides the product q1, q2 down to q sub s. Now by corollary 1.6, since p1 is a prime, this implies that p1 must divide one of the q1, q2 down to q sub s. By reordering and relabeling the q sub j's, if necessary, we can assume that p1 divides q1. Now, since p1 and q1 are both prime, this implies that p1 is equal to plus or minus q1. Therefore, substituting into the above equation, we obtain plus or minus q1, p2, p3 down to p sub r is equal to q1, q2, q3 down to q sub s, and canceling q1 from both sides, we obtain plus or minus p2, p3 down to p sub r on the left side, and then q sub 2, q sub 3 down to q sub s on the right side. Now looking at this equation, well, p2 divides the left side, and so therefore p2 must divide the right side, q2, q3 down to q sub s. And by corollary 1.6, this implies P2 must divide 1 of Q2, Q3 down to Q sub s. And as before, by reordering and relabeling the Q sub j's if necessary, we can assume that P sub 2 divides Q sub 2, which, as above, implies that P2 is equal to plus or minus Q2. And so substituting into the above equation, we obtain plus or minus Q sub 2, P3, P4 down to P sub r is equal to Q2, Q3, Q sub 4 down to Q sub s. So we have a Q sub 2 on both sides, and we can cancel that to obtain plus or minus P3, P4 down to P sub r is equal to Q sub 3, Q sub 4 down to Q sub s. Now continue this procedure. In the case that r is equal to s, then we obtain the required conclusion. P1 is plus or minus Q1, P2 is plus or minus Q2, all the way down to P sub r is plus or minus Q sub r. It remains only to show that r is equal to s. And to prove this, we'll use a proof by contradiction. So we'll suppose that r is not equal to s, so that either r is greater than s or r is less than s. We then need to derive a contradiction in each of these cases. So first suppose that r is greater than s. Then, after carrying out the above procedure s times, we will have canceled the first s primes, resulting in the equation plus or minus P sub s plus 1, P sub s plus 2, all the way down to P sub r is equal to 1. So we will have canceled all the q's on the right side, but we'll still be left with some p's on the left side because r is greater than s. Now, since P sub s plus 1 is a prime, this implies that P sub s plus 1 divides 1, which is a contradiction. Therefore, r greater than s cannot occur. Well, a similar argument shows that r is less than s also cannot occur, and therefore we can conclude that r is equal to s. And this completes the proof of the theorem. Now, by restricting ourselves to positive integers, we obtain a stronger version of unique factorization, and this is stated as corollary 1.9. Every positive integer can be written in one and only one way in the form n is equal to p1, p2 down to p sub r, where the p sub I are positive primes satisfying p1 less than or equal to p2 less than or equal to p3 all the way down to less than or equal to p sub r. So we basically are listing the primes in the factorization in order from smallest to largest. Next, we want to talk about primality testing. Now, this is one of the major problems in number theory, testing an integer n for primality. Now, applying the definition means we would need to check each number between 1 and n to see if it's a divisor. However, in the case that n is composite and n is equal to a product ab, then one of a or b must be less than or equal to the square root of n. Otherwise, the product ab would be greater than n. And this is the justification for the following result. So this is theorem 1.10, which states for all integers n greater than 1, if n has no prime factor less than or equal to the square root of n, then n is prime. So to prove this, first write out the symbolic form for all n greater than 1. If n has no prime factor less than or equal to the square root of n, then n is prime. To prove this, we'll use a proof by contradiction. So as usual, we start by supposing the result is false. Equivalently, we suppose the negation is true. The negation of the statement is there exists an n greater than 1 such that n has no prime factor less than or equal to the square root of n, and n is not prime. So we suppose there exists an integer n greater than 1 such that n has no prime factors less than or equal to the square root of n, but n is not prime. We then need to derive a contradiction. Now, since n is not prime, then by corollary 1.9, n is the product of at least two primes, so n can be written as p1, p2 down to p sub r for some r greater than or equal to 2 and positive primes p1, p2 down to p sub r. By the hypothesis, n has no prime factors less than or equal to the square root of n. So for each I, p sub I is strictly greater than square root of n. So then n, which is the product p1, p2 down to p sub r, has to be greater than or equal to p1 times p2, since there are at least two primes. And each of p1 and p2 is strictly greater than square root of n, so this will be greater than square root of n times square root of n, which is equal to n. So now we've stated that n is strictly greater than itself, and this is a contradiction, and thus the result is true. As an example, to prove 199 is prime according to the theorem, it suffices to show that 199 does not have any prime factors less than or equal to the square root of 199, which is approximately 14.1. So it suffices to show that none of 2, 3, 5, 7, 11, and 13 are factors of 199. So after verifying this, we can then conclude that 199 is indeed prime. Now, the result in the theorem can be used to construct a table of primes using what is called the Sieve of Aristocenies. We start with a table of the integers from 2 to n, and for each prime p less than or equal to the square root of n, we remove all the multiples, 2p, 3p, and so on. The remaining integers must all be prime. Now, the efficiency of the Sieve of Aristocenies is related to the number of primes less than or equal to a given integer. For any positive real number x, the number of prime numbers less than or equal to x is denoted by pi of x. The function pi is called the prime number theorem. And here's the graph of pi of x for x between 1 and 100. So pi of x will be a piecewise linear function. And here's the graph of pi of x for x between 1 and 1,000. It starts to get a little smoother. There is no elementary formula for pi of x. However, the long-run behavior of pi of x is given by the prime number theorem, which was proved independently first by Jacques Hadamard and Charles Jean de la Vallée-Poussin in 1896. And the prime number theorem states, if n is a large positive integer, then the number pi of n of positive primes less than or equal to n is approximately equal to n divided by natural log of n. More precisely, we can conclude that the limit as n tends to infinity of pi of n divided by n over the natural log of n is equal to 1. And the theorem basically says that over a large range, the graph of pi of x will resemble the graph of x over ln of x.